Good morning, students. Welcome back to session 3 of linear transformations. Say, suppose we have the transformation T belongs to E of V. Then we know that T can be completely determined by its effect on a basis of V. Okay, so if T belongs to E of V, then T can be completely determined by its effect on a basis of V. For example, suppose Vf is the vector space, say of dimension n. Say, and let V1, V2, etc. Vn be a basis of V. Now, T is a mapping from T belongs to A of V means what? T is a mapping from V to V. Now, if V1, V2, etc. Vn is a basis of V means these are elements of V. Therefore, T of V1, T of V2, etc. T of Vn, again they are all elements of V only. Okay, but these are the basis of V. Okay, therefore each of these elements T of V1, T of V2, etc. T of Vn can be written as a linear combination of basis elements, say V1, V2, etc. Vn. So let us try to write this. Say T of V1. So T of V1 as this is equal to, say alpha 1 1 V1 plus alpha 1 2 V2, etc. Say alpha 1n Vn. Now similarly T of V2 is also element of V. So T of V2 is equal to, say alpha 2 1 V1 plus alpha 2 2 V2, etc. alpha 2n Vn. Likewise, so T of the last element Vn can be written as, say alpha n1 plus alpha n2, alpha n1 V1, alpha n2 V2, and so on, alpha nn Vn, where each alpha is j are elements of F. Okay. Now we have a system of equations. T of V1 is equal to T of V1 is equal to this, T of V2 is equal to this, T of Vn is equal to this. So this system of equations can be written compactly as, say, general element T of Vi is equal to, T of Vi means what? Summation j is equal to 1 to n alpha ij Vj. I takes the value from 1 to etc. up to n means T of V1 is what? Say alpha Vi means 1, alpha 1 1 j is 1, alpha 1 1 V1, alpha 1 2 V2, alpha 1 3 V3, etc. alpha 1 n Vn. Similarly, T of V2 is alpha I is 2, alpha 2 1 V1, alpha 2 2 V2, and so on. Okay, so now you call this as number 1. Now the ordered set of n square elements. How many elements are there here? Alpha ij's are n square elements because I takes the value from 1 to n and j also takes the value from 1 to n means there are n square elements alpha ij in F. These alpha ij's completely determines T, our transformation T. So these n square elements alpha ij definitely determines our transformation. So now if V is a vector space of dimension n and if V1, V2, etc. Vn are basis elements of V, then as the matrix of T is nothing but alpha ij, 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to n, or simply this can be written as, say alpha 1 1, alpha 1 2, etc. alpha 1n and alpha 2 1, alpha 2 2, etc. alpha 2n, and so on, alpha n1, alpha n2, and so on, alpha nn. So these are the n square elements which completely determine T, means whatever the properties of T has to be, whether it is singular or non-singular or whatever the property of a T, that can be determined only through this matrix. Okay, This is called the matrix of the linear transformation T. Okay, matrix of the linear transformation T. Now the question is, so we find the matrix of T relative to the basis V1, V2, etc. Vn. Related to the basis V1, V2, etc. Vn. Now the question is, can the matrix of a linear transformation T changes if the basis of the vector space changes? Okay, understand this? So this matrix obtained by fixing the basis V1, V2, etc. Vn of V. So if you change the basis, say you know that for any vector space there may have more than one set of basis elements. Okay, for any vector space there may have more than one set of basis elements. For example, you can see that for R3, say 1 0 0, 0 1 0, 0 0 1 is also a basis. Again 1 1 1, 1 1 0, 1 0 0, it's also a basis, right? So but the number of elements in any basis will be the same. So now the question is, can the matrix of linear transformation changes? Okay, so if the basis of a vector space changes, the answer is yes. It can be observed through the following example. Okay, now let us take the example. Say I taken V to be set of all polynomials over F such that degree of P of x is less than or equal to n. Okay, these are the polynomials of maximum degree n minus 1. I'll define a transformation T from V to V by T of P of x is d by dx of P of x, means T is nothing but the derivative operator. You know that differential operator is a linear operator, because d by dx of P of x plus Q of x is d by dx of P of x plus d by dx of Q of x. d by dx of alpha into P of x is alpha into d by dx of P of x. So it is linear operator. So now you need to find the matrix of T. So they asked for the matrix of this transformation T. So unless we know the basis of V, we cannot find the matrix of this transformation. Okay, so let us see which are the basis for V. So V is the set of all polynomials of degree n minus 1, means you know what is the standard basis. The standard basis for a polynomials is 1, x, x square and so on up to xn if it is a polynomial of degree n. Now it is a polynomial of degree n minus 1. So therefore the basis elements are 1, x, x square up to x power of n minus 1. So let us take V1 is equal to 1, V2 is equal to x and so on. The Vn, nth element is x power of n minus 1, be a basis of V. Okay, then look here, then T of V1, T of V2, etc. T of Vn certainly belongs to V. Okay, T of V1, because T is a mapping from V to V, so T of V1, T of V2, etc. T of Vn are also elements of V. As I said, so each of these elements of V can be written as a linear combination of basis elements. Let us try to write these T of V1, T of V2, etc. T of Vn as a linear combination of these basis elements. Say first T of 1. T of V1 means T of 1. What is T of 1? T of 1 is, so T is a differential operator, therefore T of 1 means d by dx of 1. d by dx of 1 is 0. Now 0 can be written as 0 into 1, or in the words 0 into V1 is 1. So 0 into V1 plus 0 into V2 and so on, 0 into Vn. Okay, understand now? 0 can be written as linear combination of V1, V2, etc. Vn. Next T of V2. T of V2 is what? T of V2 is x. T means d by dx of x is 1. So 1 can be written as 1 into V1, because V1 is 1. 1 into V1 plus 0 into V2 and so on, 0 into Vn. Next T of V3. T of V3 is what? T of x square. T of x square is 2x. Now 1 is not there, 0 into V1 plus 2 times into x means V2 plus 2 times V2 and so on, etc. 0 times Vn. Likewise, the nth element T of Vn can be written as T of x power of n minus 1. So if you differentiate this, n minus 1 into x power of n minus 2. So it gives 0 into V1, 0 into V2, etc. Last but one term, 1 into Vn minus 1. Okay, next is 0 into Vn. Okay, so now we got the system of equations. So therefore the coefficient of matrix is the coefficient matrix is the matrix of the linear transformation. Therefore the matrix of T in the given basis is M1 of T is what? First one is say 0 0 0 etc 0 0 0 etc 0. Next is 1 0 0 etc 0 1 0 0 etc 0. Next 0 2 0 0 etc 0 0 0 n minus 1 0. This is the matrix of T. So every property of a transformation T being hidden in this matrix. So suppose they will give some transformation and you are asked to verify whether that transformation is invertible or non-singular. So finding the inverse of a transformation or finding the inverse of some transformation is very, very difficult. But if you know the corresponding matrix, then you know how to find the inverse for a matrix. If the inverse of the matrix exists, then we say that the transformation T has also inverse. Okay, or any property of a transformation can be verified through the matrix. Now as I said, so if you change the basis, then the matrix of linear transformation also changes. Let us find the matrix of the same transformation T, which is the differential operator, for the different set of basis elements. Okay, so let us take U1, the basis U1 as 1, U2 as 1 plus x, U3 as 1 plus x square, and Un as 1 plus x power of n minus 1. Certainly these are the basis for the vector space V. Okay, you can verify it. Now again, T of U1 belongs to V, T of U2 belongs to V, T of U3 belongs to V, etc. T of Un also belongs to V. Therefore these can be written as a linear combination of basis elements. Therefore I'll write T of U1 is T of 1. T of 1 means d by dx of 1 means 0. 0 can be written as 0 into U1 plus 0 into U2, etc. 0 into Un. Next, T of U2. T of U2 is T of 1 plus x. So 1 plus x is 1. So this can be written as 1 into U1 plus 0 into U2, etc. 0 into Un. Next, come to the here. T of U3. T of U3 is what? T of 1 plus x square. T of 1 plus x square is 2x. Now the basis elements are not of the standard form. 2x, it is not like 1 plus x. The basis elements are 1, 1 plus x, 1 plus x square. So we need to write 2x in this form only, linear combination of this form only. So for this, what I do is I add and subtract 2 for this. 2x plus 2 minus 2. So I'll take 2 into x plus 1 minus 2. Or in other words, this can be written as minus 2 plus 2 times 1 plus x. Okay. So minus 2 into 1. 1 is U1 plus 2 into U2 is what? 1 plus x plus 2 into U2. The others are zeros. 0 into U3, etc. 0 into Un. Understand now? So this is a trick here. So we need to express T of U3 as only linear combination of the given basis elements. So likewise, T of Un is T of 1 plus x power of n minus 1. 1 plus x power of n minus 1 is n minus 1 into x power of n minus 1, n minus 2. Differentiation. Okay. So this can be written as accordingly minus n plus 1 into 1 plus minus n minus 1 plus n minus 1. Add and subtract n minus 1 here plus n minus 1 into x power of n minus 2. Okay. So this is equal to, say what happens? So T of Un is equal to T of 1 plus x power of n minus 1. So this is equal to minus n minus 1 into U1, okay, plus n minus 1 into other thing is 1 plus x power of n minus 1 into Un minus 1. Okay, this is equal to minus n minus 1 into Un plus 0 into U2 and so on, plus n minus 1 into Un minus 1 plus 0 into Un. Okay, understand now? Plus 0 into Un. Because so this is Okay, can be written as, look here, the last step, this is equal to minus n minus 1 plus n minus 1 into what, 1 plus x power of n minus 2. Okay, 1 plus, so minus n plus minus of n minus 1 plus n minus 1, if you take common from these two factors, so this is 1 plus x power of n minus 2. So we have written like this. So therefore the matrix of T in this basis is M2 of T is, first is the 0 vector, 0 row, 0 0 0, next is 1 0 0, next is minus 2 comma minus 2 2 0 0, last one is minus n minus 1 0 0 etc. Last is n minus 1 comma n minus 1 0. Okay, understand this? So this is the matrix. Now we got two matrices for the same transformation. So if you change the basis, then the matrix of linear transformation also changes. Now can this matrix M1 of T, you find what is M1 of T and M2 of T for the transformation T. Now can these matrices give the same transformation T, give back the same transformation T? Yes. These two transformations, although they look different, they give the, or they represent the same linear transformation. Okay, so there must be some relation between these two matrices. Okay, so look here, the transformation is same, only if they change the basis, then the matrix of linear transformation only changes, but both the matrix represents the same linear transformation. Is there any relation between these? Yes, there is a relation that I will explain later. Okay, now see here. So from the above examples we can see that the matrix for T for two different bases used depends completely on the basis. Although they look different from each other, they represents the same linear transformation. Okay, which is T. And we can construct T from any one of them if you know the basis used in their determination. Okay, so each linear transformation T in A of V as associated with it a unique n cross n matrix that is denoted by M of T. Conversely, if A is a matrix given, say if A is a matrix, n cross n matrix with the entries Aij, then for a given basis V1, V2, etc. Vn, we can define the transformation T from V to V by how? T of Vi is equal to summation over j alpha ij Vj. Then T becomes a linear transformation on V. Okay, understand now how we can obtain the linear transformation using the basis, using the matrix. Suppose they were given the matrix, n cross n matrix, then how to know this matrix represents for a which transformation? So the transformation can be found out if you know the basis. So T from V to V by T of Vi is equal to summation over j alpha ij into Vj. Then T becomes a linear transformation. Okay. Now say we have the set of matrices, say n cross n matrices, that may be denoted by Fn. So you denote the set of all n cross n matrices by the symbol Fn. Now any two elements of Fn, Fn means n cross n matrices, any two elements of Fn are said to be equal. When you say they are equal, if they are identical. If they are identical means if you say A is the matrix with entries Aij and B is the matrix with entries Bij, then A is equal to B if each of the terms must be equal to S. Each of the terms in A and each of the terms in B must be same. Means Aij is equal to Bij for each ij takes the value from 1 to n. And then mapping, which maps for every transformation a matrix, and the mapping say phi from phi, which maps for every transformation a matrix defined by, say this is T of Vi is equal to summation j is equal to 1 to n Aij Vj. Aij as coefficient matrix. Okay, definitely is a one-to-one mapping of A of V onto Fn. because you know if V is of dimension n, how many linear transformation, what is the dimension of A of V? It is n square. So n square number of elements are there. So here too, so there is a one-to-one mapping of A of V onto Fn. Okay, if you want to show this, yes, let's verify. So suppose phi of t is equal to phi of s. Suppose t and s are elements of where t comma s belongs to A of V. Then this implies phi of t is equal to phi of s means what? Phi maps t to its matrix. So m of t and is equal to m of s. Matrix of t is say Aij, and suppose the matrix of s is say Bij, where matrix of s is Bij. Okay, this implies the matrix Aij is equal to Bij means what? Each of the terms Aij must be equal to Bij. A11 is equal to B11, A12 is equal to B12, likewise. So this implies what? Summation j is equal to 1 to n, Aij Vj is same as summation j is equal to 1 to n, Bij Vj. Okay, this implies what? T of Vi is same as S of Vi. If T of Vi is same as S of Vi, what you can say? T is same as S. T is same as S. Therefore, phi is 1 to 1. So, if phi of t is equal to phi of s, then s is equal, then t is equal to s. Therefore, phi, the mapping which maps every transformation, its matrix is 1 to 1. And also, look here. Say, and if Aij is a matrix belongs to Fn, then definitely we can find some transformation t belongs to A of V such that T of Vi is equal to what? Summation j is equal to 1 to n Aij Vj. This happens. Therefore what? Phi of t is equal to, then matrix of t is what? This Aij. So phi is a mapping which maps every transformation to its matrix. So phi of t is equal to Aij. Thus, if Aij belongs to Fn, then there exists t belongs to A of V such that phi of t is equal to Aij. Okay, actually phi is a mapping from where to where? Phi is a mapping from A of V to say Fn, where phi of t is equal to matrix of t, Aij, or matrix of t. Phi of t is equal to matrix of t. Right? Therefore, what happens? Phi is onto. Now phi is 1 1 and phi is onto. Now, so if A of is an algebra, we have proved. A of is an algebra over F, we have proved. So V is the same above mapping of A of V onto Fn to define the operations of addition, multiplication and scalar multiplication on Fn, that is set of all n-class n matrices, in such a way that Fn also becomes an algebra, okay, which is isomorphic to A of V. So we can define the addition, multiplication and scalar multiplication in Fn so that Fn also becomes an algebra. If Fn becomes algebra, then what will happen? We have a mapping phi from A of V to Fn, which is 1 1 and onto. Therefore, Fn also becomes S algebra, and A of V and Fn are isomorphic. They are isomorphic to each other. So how do you define the addition then? So let us take A is equal to Aij is one matrix, B is equal to Bij is another matrix. This means they are the elements of Fn. Such that the matrix A corresponds to the transformation T and the matrix B corresponds to the transformation S. Then by definition, T of Vi is what? Summation over j, Aij into Vj. Likewise, S of Vi is what? Summation over j, Bij Vj. So that matrix of T is A, matrix of S is B. Okay. Now T plus S of Vi is what? Since T and S are linear, T of Vi plus S of Vi. So this is equal to summation over I, Aij Vj, summation over j, Bij Vj. So this is equal to summation over j, Aij plus Bij into Vj, means T plus S as the matrix Aij plus Bij. Thus the mapping phi maps T plus S to Aij plus Bij. Therefore we have defined the addition in Fn as Aij plus Bij is equal to Aij plus Bij. That is matrix of T plus matrix of S is matrix of T plus S. Okay. Next is, what is the next operation? We need the operation as multiplication, because we need to show it's an associative algebra. It's an algebra means associative ring. It is an associative ring. So we need ring means we need multiplication operation also. So let us define the multiplication operation in Fn as, okay, we know that the product of two transformations is S into T of Vi is S of T of Vi. S of T of Vi is what? Summation over J. Instead of J, I just taken K. Summation over K, Aik into Vk. This is equal to summation over K, Aik into, since S is linear, because S belongs to A of V means it is a linear transformation. So S of Vk. So this is equal to summation over K, Aik into, S of Vk can be written as summation over J. So S of Vi is summation over J, Bij, Vj. So K means summation over J, Bkj, Vj. So rearranging the order of summation, we get S into T of V is equal to summation over J, first one, into summation over K, Aik into Bkj into Vj. So this is, therefore this is the matrix of S into T. Therefore St corresponds to the matrix summation over K, Aik into Bkj. Accordingly we define the multiplication in Fn as Aij into Bij is equal to summation over K, Aik into Bkj. Thus matrix of T into S is matrix of T in, this is matrix of T into S. So therefore matrix of T into S is matrix of T into matrix of S. So we define the we define the multiplication of matrices also using the transformations. Now third one is, so now it need to prove it's an algebra means it must be a vector space. So vector space means we need addition binary operation, which is scalar multiplication. So let's define what is meant by a scalar multiplication here. Okay. So if C belongs to F, then by the definition of scalar multiplication in A of V, what will happen? C into T of Vi is C into T of Vi. This you know. Okay. So this is equal to C into summation over J, Aij, Vj. Okay, this is called summation over J, C into Aij into Vj. It doesn't affect. C I taken inside. Thus C of Aij is equal to what? C of Aij is C into Aij is C matrix of Cij. Cij. So we have defined the scalar multiplication. Okay, that is if A belongs to Fn and C belongs to F, that is if A belongs to Fn and C belongs to F, then C into A is a matrix obtained by multiplying each element of A by what? C. How do you get C into A? You have to multiply each element of the matrix A by the constant C. Thus we have matrix of C into T is equal to C times matrix of T. Thus we have defined what is meant by addition, multiplication and scalar multiplication in Fn in such a way that all of these basic operations are preserved under the mapping as phi, which maps T to matrix of T. Thus the mapping T to matrix of T, that is phi, is an isomorphism of A of V onto Fn, because all the operations are preserved. Okay, as algebras, that is isomorphism as rings as well as isomorphism as vector spaces. Means this is a isomorphism means what? We need to verify the homomorphism condition for addition, multiplication, also for scalar multiplication. That's why, so this mapping is an isomorphism of A of V onto Fn as algebras, that is isomorphism as rings as well as isomorphism as vector spaces. So the above discussion can be summarized as, see, look here, the above discussions can be summarized as, so as a theorem, the theorem states the set Fn of all n cross n matrices, the set Fn of all n cross matrices over F is an algebra over F. We can show this, we can verify all the properties of a algebra can be verified through Fn. And also if V is finite dimensional vector space over F, okay, then A of V and Fn are isomorphic as algebras over F. Okay, if V is a n-dimensional vector space over F, then A of V and Fn are isomorphic as algebras over F. Okay, this is a famous theorem. Okay, so now this is the statement. Now, so what is the zero element then of this algebra? Zero element of this algebra Fn is the zero matrix having all its entries are zeros only. We denote it by the symbol bold 0 or big 0, that's all. And the unit matrix having the entries 1 0 0 0 1 0 etc 0 0 1 0 0 1, okay, is the unit matrix of Fn under multiplication. We denote this by the symbol I. Okay, this is a standard convention, you already used this type of things. Okay, next, if C belongs to F, then the matrix C into I is what? Having C's on the diagonal. So multiplying throughout by C here. So C, 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 etc. C on the diagonal place is called this is called what? Scalar matrix. The matrix A belongs to Fn is called triangular. When you say it's a triangular matrix, if all the entries above or below the main diagonals are zeros. Okay. If all the entries on the main diagonal, all the entries above or below the main diagonal are zeros, then it's called the triangular matrix. Okay, so it look like, say this is the matrix. If you want to write, say this is A11 0 0 etc 0, say A21 0 0 etc 0, likewise AN1 AN2 etc ANN. Sorry, A11 A22 ANN. Okay, likewise you can write this, you make these to be zeros and yes, and you can have elements like this, upper triangular, lower triangular matrices. And the matrix A belongs to Fn is said to be invertible or non-singular if there exists some matrix B belongs to Fn such that A into B is the identity matrix, or similarly B into A. We need to verify both, because in the matrices you know that AB is not equal to BA generally. Okay, that's why we need to verify whether A into B is I and B into A is also I. Okay, and also since A of V and Fn are isomorphic, it is clear that T belongs to A of V is invertible if and only if the matrix M of T has an inverse in Fn. Means, as I already said, if you want to verify the transformation T as T is invertible or non-singular, then to verify whether the transformation is non-singular or invertible, it's very difficult task. So instead if you find the corresponding matrix, it's easy to check whether the given matrix is invertible or not. Yes, if the matrix invertible, we say that transformation is also invertible. So how to find the then what will be the inverse of the particular transformation T means? So you will get the inverse of a matrix. Say, look here, say we have, suppose the transformation is T. T is matrix of T. Okay, now suppose T is invertible, T inverse exists, say, so matrix of T inverse. Now, so if matrix of T has an inverse, then we say T inverse exists only. Then how do you define particularly that transformation T inverse? How to obtain T inverse? Then we can easily obtain through M of T inverse. So you know that there is a one-to-one correspondence between set of matrices and set of linear transformation, set of matrices and set of linear transformation. From this matrix you go back to linear transformation. Say S is the linear transformation. That linear transformation S is nothing but the inverse of T. Okay, understand now? So from the matrix, say given Aij is the matrix. From this matrix, definitely if you know the basis, then you can reverse it to get the transformation T. That say transformation S, that transformation S is nothing but the inverse of this. Okay, understand now? So finding the inverse of a transformation is very easy if you know the matrix of that transformation. Okay. So as I already said, for a transformation, if you change the basis of a vector space, the matrix of linear transformation also changes. Okay. So whether they are all yes, is there any relation between them, that we will answer it in the next class. Okay. Thank you.